Welcome to the final video in our series on elementary group theory. It's been quite an exciting journey, and in this last video, our goal is going to be to echo the discussion of the very first video. There, I told you that there was a connection of groups to symmetry and to symbolic manipulation under formal rules. What are these connections exactly? You know, we often motivate the study of groups via the study of symmetry. We say over and over and over again, groups encode symmetries. What does this actually mean? It is rarely, if ever, made explicit. So today we're going to do exactly that. We are going to make explicit the connection of groups to symmetries, groups to symbols, and thus to each other. And we're going to connect algebra and geometry and see how groups sit in the middle of that picture. And the way we're going to do it is to introduce a few new notions, and then finally to use everything we've found so far to talk about the group we introduced in the very first group theory video, which I'm now in a position to call D3 for you. The dihedral group on three symbols, or as we introduced it originally, the group of symmetries of an equilateral triangle. First, we're going to talk about symmetries. And to start off this discussion, I'm going to introduce a new notion to you, a new way of visualizing the internal structure of a group. And this is called the Cayley graph of a group. So what we're going to do is the following. We're going to start with a vertex for each element of a group. Now we're going to draw an edge between two vertices if you can get from one to the other by multiplying by a generator of the group. So suppose that we have some element here at this vertex we'll call A, and suppose we have some generator X, and we have some other element B here at the end. Then what this would indicate, I'll put a little arrow so you can tell in which direction we're multiplying. A times X will give us B. For some generator of the group X, right? So X belongs to some big set X, where our group G is generated by the big set X. Notably, every Cayley graph is going to be one connected component. And the reason for that is simply that the generators generate the group. So there can't be some random, we can have some shape over here, and there's this random element over here which isn't connected by an edge to any of the other group elements. That doesn't make sense. That contradicts the definition of a generator. Now for our examples, we're going to use the groups last time that we found presentations for in terms of generators and relations. This will make things easy for us. So we'll start with ZM. So last time we showed that it has this set of generators and relations which give you a presentation of Z sub M, the cyclic group of order M. And all we're going to do, because there's only one generator, so we're going to have our M elements, so I'll arrange them in a little M-gon here, little dot dot dot, dot dot dot. Alright, and we're going to pick a vertex to start with here. Let's just do this one for arbitrarily. Now we're going to multiply by B. And this will get us to the next vertex. And we'll multiply by B again, times B, equivalent to multiplying by B squared, but in any case, times B again, times B again, times B again, times B again, etc., etc., etc. And after exactly M times, what do we expect to happen? Well, because B to the M is in Y, we know that B to the M is equal to the group identity, which means we should end up where we started. So after exactly M times of multiplying by B, we should end up exactly at this spot where we started. In other words, the Cayley graph of this group is just going to be a regular M-gon. Well, it doesn't actually have to be regular, but it looks prettier if it's regular. Alright, for our next example, Z6. We showed last time that this is a presentation of the group Z6, two generators, and the relations A squared, B cubed, and this commutativity relation here. So, what are we going to do? Well, I'm going to use colors now because it's going to be much easier to see if I use colors. So let's start with b cubed. We're going to multiply by b and represent that as a purple edge. So let's say we start at this element. And for visual purposes, I'm going to go across here, like so. We're going to say that this is multiplying this element by b to obtain this element. Now once again, we're going to multiply by b. And then once more, and we should, because b cubed is equal to the identity according to this relation, we should end up with a little triangle. We should end up where we started. And this should be true anywhere we start, right? So it's going to be true here, and it's going to be true here, and this is already obvious from that. But we'll want to draw another triangle so that it's clear what's happening with these three elements. Okay, so I just drew our other little triangle here. Now we have to take care of multiplying by a. Now recall, a squared is equal to the identity. Don't make fun of me for using pink and purple. A squared is equal to the identity. So multiplying by a twice should get us back to where we start. So we're going to represent this in this way. We're going to draw an edge from here across. And I'm not going to direct the edge because multiplying by a, and then because it's the same in both directions, right? In either case, if you multiply by a, you traverse the edge. We're going to do the same thing here. And we're going to do the same thing here. And so we see that the b cubed and a squared relations are already satisfied. And the only thing we have yet to show is that this is satisfied. All right, let's start at an element and let's do it this way. Let's first multiply on the right by b, which will get us to here. Now let's multiply on the right by a. That will get us right here. Now multiply on the right by b inverse. That will take us backward along this edge, right? And now multiply by a inverse, which is the same as a, and we end up exactly where we started. And you can do this with any of these 6 elements, and you see because of the symmetry here, it's going to work from any point. So we have created a Cayley graph which successfully represents this group Z6. Of particular note is that when you draw the Cayley graph of this group, it's more easily understandable why Z6, and I told you last time this was an unusual coincidence, is equal to, or rather is isomorphic to, the direct product of Z2 and Z3. We can see this right at work, where we have one triangle, one copy of Z3 if you will, and another triangle, another copy of Z3. And they're related how? By these cross relations where if we multiply by 1, or by a, and then multiply by a again, we get back the identity. Or in additive notation, this would be the same as adding 1 and then adding 1 again, which is mod 2 congruent to 0. So you can visually see how Z6 here is isomorphic to the direct product of Z2 and Z3. You can see already how valuable this tool is. Now last time we looked at just this presentation, right? We said the group with these generators and relations, simply by taking out that what I called the abelian relation in Z6, we get a group which is not only infinite but also non-abelian. So let's just briefly look at what the graph of this might look like. Well, once again, you're going to have some triangles, right? Because b cubed, say we multiply by b 3 times, it's going to be the identity, right? And this has to be true starting anywhere, starting here, here, here. All right, and then suppose we multiply by a, I'll represent that with a dashed line here, and then we're going to have another triangle. And with the Z6, we had a connection between these two triangles, right? That the corners of these had to be connected in a very special way, and that was defined by our third relation. But without that third relation, what's going to happen here? Well, suppose you start here, and similarly to before, you multiply by B inverse. Well, that's going to get you here. Now A inverse, which is just A, this is going to get you here. Then multiply by B, and then multiply by A again. Now before we had a condition which said that this has to get us back to here. Well, but now it doesn't, right? Now, in general, that's not true. We don't have a relation specifying that. So when we multiply by A again, we're going to end up on a new triangle. And you can see how this process, starting at every vertex, really, is going to give us, a new triangle each time. And so it's just going to split and split and split infinitely. And it should be pretty clear why this is not abelian, because this relation isn't in it, and why it's infinite, right? Because we don't have a connection saying once you go around here and around here and around here that you come back. You can just keep going. The last group we talked about last time was Q8, the quaternion group. Recall this is plus or minus 1, plus or minus I, plus or minus j, plus or minus k. And we said that it can be given by this presentation in terms of 2 generators and these 3 relations. Let's see what the graph of this looks like. Alright, so this is the simplest Cayley graph representation I have been able to find for Q8. It's a little bit of a trial and error situation and how to draw it so that it looks the neatest. So we have one generator represented by the pink, and again the other one by purple. So let's see if this really does hold up. So suppose we have a to the 4th, right? So we multiply by a, then multiply by a, then a again, and then a final time. We do indeed end up where we started. And in fact, this is also true for the pink. Why? Remember that a squared b to the negative 2 is equal to the identity is equivalent to a squared equals b squared, which is to say that b to the 4th is also going to be a to the 4th. So b to the 4th is also the identity. So both of them form these closed rectangles, as we can see. Alright, what about this second relation? A squared b inverse squared. Well, if we start here and we take a, which I'm calling purple, I believe. So if I take a and then I take a again, and then I take b inverse and b inverse again, where do we end up? Exactly where we started. Equivalently, I could have said, let's take b inverse, and then take b inverse again, and then take a, and then take a again. And that does get us back to where we started. And once again, by symmetry, you can see that this is true at every point. Now the question is, does it satisfy the last one as well? Well, let's see. Starting here, I take A, then I take B, which takes me to here. Then I take A again, which is down to here, and then I take B inverse, which gives me here. And let's do it in the backward order just for fun. Let's go B inverse. B inverse takes us to here, then to A, then by B, then by, oops, sorry, no, that was by B, and then A again. So B inverse, A, B, A. And we're good. We see that this Cayley graph very succinctly describes what we, at greater length rather, elucidated last time in terms of generators and relations. Isn't that neat? Now, there is a further connection of groups to graphs. In fact, there are many deep connections between these two things, but I particularly want to draw your attention to the following result from graph theory, which is that given any finite group, we'll say G, we can construct a graph whose automorphism group, this is the automorphism group of a graph now, whose automorphism group is isomorphic to that group. This is a pretty interesting result, but it gets even more interesting when you start thinking about how graphs can be embedded into space, right? Graphs do not have a notion of distance in the way that normal geometric objects do, right? When we connect vertices with an edge, this is the same as this, is the same as this. In graphs, all that really matters is the connectivity properties. However, they can be embedded into space. So you might think if groups are connected to graphs and graphs are connected to space, then every finite group might just have a connection to some geometric object. Let's follow this trail further. Alright, let me remind you of a quick fact that we proved a few videos ago, and one of the most important results in this whole series. Cayley's theorem, a name you should get used to hearing. Every group G is isomorphic to a group of permutations. Particularly, if G is finite, then G is isomorphic to a subgroup of the symmetric group on n symbols, where in this case n is equal to the order of G. One more fact I want you to keep in mind for a moment. We found another group, Pn, which was isomorphic to Sn. So we were able to study the structure of the symmetric group via its isomorphic relationship with this this group of n by n matrices. Okay, so keep that in mind. Now we're going to define a new object called the n-simplex. The n-simplex is a geometric object that for certain values of n you are already quite familiar with. So we're going to define it as the convex hull, I'll explain what that means in a second, convex hull of a certain set of vectors. And these vectors are going to be the basis vectors e1, e2, all the way up to e sub n plus 1 in R n plus 1, right? So e sub I is in R n plus 1. We're going to take the convex hull of this set of vectors. What is the convex hull? This is just a linear combination Ci, Ei, over all I guess if you want to be detailed, I equals 1 to n plus 1, such that it's a set of all such linear combinations such that each C sub I is between 0 and 1. Now, this looks more complicated than it is. All this is saying is that these vectors, equivalently, we can think of them as n plus 1 tuples, are just simply points in space, and they define the corners, if you will, of some convex geometric object. Convex meaning not like this, right? We can any point that is any 2 points that you have that is in the shape. Say, this is a triangle for instance, any 2 points you have in the shape, every point along the line in between them is also in the shape. That's what we mean by convex. So we're taking the convex hull of this set of vectors, and that is going to give us a shape called the n-simplex. And as I alluded to before, you're already familiar with this in low dimensions. Namely, the 0 simplex is just a point. The 1 simplex is going to be a little line segment, 1 simplex. A 2 simplex is going to be a triangle filled in, 2 simplex. A 3 simplex is going to be a tetrahedron with the volume included, right? 3 simplex. And so on. So basically, an n-simplex is just the n-dimensional generalization of a triangle. Very simple, but very important shape. In particular, note how we can create this using the basis vectors. So I drew it for you before without the basis vectors, but now let's use them. So for the, this is in R2. In R2, we're going to have the 1 simplex defined by the convex hull of these 2 vectors, which is going to be what? It's going to be every vector in between here along this line. Equivalently, it is all the points contained between these 2 lines, and between these 2 points, which is a line segment. So you get your one simplex in R2. Similarly, suppose we're in R3 and we have our three basis vectors I hat, j hat, k hat, and we'll put little points here. We take the convex hull, what are we going to get? We're going to get a triangle going between these 2 points and then filled in. So we can define it, importantly, via the basis vectors in a space 1 dimension higher. Okay, time to think critically about this. So, we have our group of permutation matrices P sub n plus 1. And for each element, each matrix in this group, it's going to consist of a matrix of 1s and 0s, you know, a little 1 here, a little 0 there, whatever. It's going to consist of 1s and 0s, some permutation of the column vectors, which we can think of as a permutation of the basis vectors, right? Each column is going to be one of the basis vectors. Well, this is a map whose determinant is plus or minus 1, minus 1 corresponding to a reflection where you reverse the orientation of your coordinate system, and plus 1 to something which corresponds to perhaps a rotation where we preserve the orientation. But notice that because the way this acts on a vector is just going to be to permute the elements of that vector, then we have to have that the size of whatever the output is equal to the size of the input. The norm of the vector has to be the same, right? Norm of the vector is going to be the sum of the components squared and then the square root, right? But if we just simply switch, if we simply permute the components of this vector in some way, this sum and thus the square root is not going to change at all. So, and one more fact also, m acting on the 0 vector is just going to be the 0 vector. So now what we have here is a distance preserving transformation which fixes the origin. In other words, m, in virtue of being part of this permutation group, is an isometry of Rn plus 1. Moreover, because our n simplex is going to be defined in terms of those basis vectors, then any element in this group is going to also be an isometry of Rn plus 1, which maps the n simplex, as we defined it, to itself. This is critical. Now the group of symmetries of the n simplex is going to be the set of all possible mappings from the n simplex to itself. So you can think of this, all possible mappings phi to itself, nice little notation there, which is also an isometry. But we've just found this. So pay attention here. The group of symmetries of the n simplex is P sub n plus 1. And this means that up to isomorphism, it is the symmetric group on n plus 1 symbols. Now, let's connect the dots. If every group, every finite group anyway, can be embedded into the symmetric group on n symbols, and the symmetric group represents the group of symmetries of a geometric object in space, then transitively, we have that every finite group can be embedded isomorphically. So this is true up to isomorphism inside a group of symmetries of a geometric object. So every group talks about the symmetries of some geometric object. And in fact, if you're wondering if this generalizes any further, it does. It's much harder to show, but in fact, every finite group is going to be the group of symmetries for some object, the full group of symmetries. So we see that groups and symmetries truly are deeply connected, and wherever there is a group, there are symmetries in the old-fashioned sense. Our next matter of business is going to be to show that this is a two-way street. The symmetries also imply groups. This is really the meat of it. How does symmetry imply group? So let X be some set, be a set of anything. Doesn't matter what the elements of this are, it's just a set. And let Y be some subset of X, not necessarily the whole set X. And then let phi sub I denote a family of bijections indexed by some set, say capital I. This is some family of bijections from X to X. So we'll say phi sub I goes from X to X, the bijection. And now we're going to require that for each of these bijections, that phi sub I of Y is equal to Y. In other words, if you have some element in Y, it is going to get mapped under every one of these bijections to another element in capital Y. So it is a bijection from X to itself, essentially preserving Y. And why am I saying this? Because this is the most general definition of symmetry I can come up with, in a sense. We have some change represented by our map phi sub I. In fact, we have a collection of such changes, such transformations, if you will. And then we have something which stays the same. And if you really reflect on this, this is the heart of symmetry, right? In rotational symmetry, say, in a geometric sense, we have a set, right? The set of, say, we're just considering the vertices, or it doesn't really matter. In any case, when we rotate, we're applying some change to, let's say, the whole plane. We're doing coordinate geometry here. There's some underlying grid, and we're applying some change to the whole thing. And of course, this point is not going to get mapped to itself. It's going to get mapped to some random other point in the grid. However, points in this triangle get mapped under this rotation by 120 degrees, say. It's an equilateral triangle, to other points in the triangle. In other words, this triangle is invariant. And so what I'm trying to show here is that this is the most general definition of symmetry, that we have some family of changes which leave something unchanged, right? There's some invariant set, which is going to be Y. And now we're going to show that this leads to a group very naturally. All right, so as you may have guessed, our group operation, well, first of all, our group is going to be this family of bijections. And the operation is going to be function composition. Right? We've seen this operation over and over again. It's very important. So, first of all, let's check closure. Phi sub I composed with phi sub j. Clearly, this is going to be a map X to X, right? A map X to X composed with a map X to X is going to be another map X to X. So I'm not worried about showing that, but let's consider what happens when you have an element in let's say Y1 is in Y. Well, this is equal to phi I of phi j of Y1. Now we know that this map, because it's in the set, maps you to an element in Y, which we'll call Y2, not necessarily Y1. So this is equal to phi sub I of Y2. Since Y2 is in the set big Y, this is also going to map us to another element, you can call it Y3, which is once again in Y. So what we get is that the composition is a bijection X to X, which preserves for all elements Y1 in Y. It sends them to another element, namely Y3 in Y. So we have closure, which is always the first thing we should check. The second thing we would want to check is associativity. Now this is always true for function composition. We've talked about this before. Both are equal to, or both are really defined to mean phi of I of phi of j of phi of k of, whatever your input is. both are defined to mean this, so that you're going to get generalized associativity with composition of functions. So associativity is not going to be a problem, and we can move on to the next axiom. 3, an identity, right? We just have the identity bijection, right? Identity from x to x, where id of x for all x in big X is equal to little x, right? Just sends every element to itself. Clearly, this map composed with any phi sub I is going to be equal to phi sub I composed with the identity is going to be equal to phi sub I. So we have an identity element in our group. And last but not least, inverses. To check that we have inverses, we want to show that there exists some phi sub I inverse such that this is true, right? And obviously this phi sub I inverse does exist. Why does it exist? Because phi sub I is a bijection. Whenever you have a bijective function, this implies the existence of an inverse function such that the composition is the identity. And we have shown that we have inverse elements in our group, and hence that we do indeed have a group. So the idea of simply applying a transformation and some part of our set under consideration, talking in as general terms as we can here, something stays the same. Something changes, well, something else stays the same. This is what symmetry is, and simply by considering the composition of these transformations, we have just formed a group. So we see that symmetries do indeed always, in this generalized sense, imply groups. And now we see that this is a two-way street, and that symmetries and groups are really talking about the same thing, something we've hinted at all along but have never really made explicit. Now we're going to next jump into what the connection of groups is to symbols, and then the implied relationship between symmetries and symbols. So this entire time we've really been operating under the assumption that it is valid and helpful even to talk about groups in terms of symbolic manipulation and formal rules, right? Where we'll often talk about groups, just as we did last time, in terms of, say, the generators A and B and some set of relations. A squared is equal to B to the fifth, say. Where it's valid to say, well, we can express group elements in terms of these two things, and then these two things play together in this way, or we give some list of identities satisfied by elements in the group. And this was our group presentation, right, in terms of generators and relations, saying that we can indeed define a group this way, and moreover, free groups, which were the basis on which we talked about group presentations. Free groups are connected to every group in the sense that every group is the homomorphic image of a free group. And indeed, it is generally true that every group has a presentation, right? At the very least, in terms of a set of generators which includes every element from the group, right? But there may be a much simpler, and usually is a much simpler set of generators. But there is always going to be a presentation for your group. So it is always valid to talk about groups in terms of generators and relations. In other words, in terms of symbols and rules governing those symbols, right? This is the heart of algebra right here, just as symmetry is in some sense the heart of geometry. Symbols and rules are really what algebra is made of. And so now we can see, because every group has a presentation, because every group is a homomorphic image of a free group, we see some really profound dualities here, right? We showed a second ago that symmetries and groups were a two-way street. And now we see this is also true with groups and symbols, right? Groups and symbols and rules, right? That these two things are also the same thing. And transitively, that symmetries and symbols are linked in this profound way, that algebra and geometry are linked in this profound way that is groups describing both of them simultaneously. So now, as our final example in our series on elementary group theory, I give you the dihedral group, Dn. And what is this going to be? This is simply going to be the group of symmetries for a regular n-gon in the plane. So for instance, D4 is going to be the group of symmetries of the square. So that's going to include this reflection, that reflection, and then also all the rotations in both directions. And this ends up being, including the identity transformation, D4 is an order 8 group. And we talked about this last time when we were trying to decide if our unknown group was Q8 or D4 or whatever. And I said I was going to talk more about the dihedral group this time. So Dn is going to be the group of symmetries of a regular n-gon. And it's a colorful little group. In particular, because I brought it up as a motivational example, I would like to focus all of our effort on the special case of D3, the group of symmetries of the equilateral triangle. So the first way to characterize D3 is as a group of symmetries, right? So this is exactly the example I gave in the first video, and I'm trying to keep notation that is relatively consistent, even if maybe not used conventionally. So we have the identity transformation, we have a rotation in this direction once, we have a rotation the other direction once, notice that that's the same as rotating twice in this direction, and then we have 3 reflections, right? Reflection across line A, which I'm calling just A, B, which is just a reflection across line B, and C, which is just a reflection across line C. So this is D3 as a group of symmetries. So our second characterization is going to be as a Cayley table. So we have our multiplication here, and we see a bunch of eyes along the center, or rather the diagonal, and this just corresponds to reflections being idempotent in this sense that 2 reflections gives you back the identity map, right? Doing the same reflection twice just does nothing. And then you also see that various ways of composing reflections will give you rotations. And this is actually an interesting but sort of related point, and that is that even in higher dimensional space, rotations can always be broken down into an even number of reflections. And so we see here composing these reflections ends up giving us a rotation. So that's just a fun fact. And you see basically what the deal is with this. We can study the anatomy of the group via its multiplication table. Our third way of viewing D3 is as a subgroup of the symmetric group. And in fact, you'll notice very quickly that in this special case, D3 is actually equal to the symmetric group on 3 symbols, right? Because any way of switching 2 of these vertices is going, which defined by the symmetric group elements, right? Or any way of permuting them rather, is going to give you also an isometry, which is a rare fact that only happens when n equals 3. But we see that the dihedral group can, in dimension 3, dimension if you will, degree I guess would be a better word, can be characterized in terms of a subgroup of the symmetric group, and in this case it is equal to the symmetric group itself. Alright, so our next way of characterizing D3 is as a Cayley graph. So you might think this looks just like Z6, they must be isomorphic, right? Wrong. They are not isomorphic. They do look similar, but one of the triangles here its direction is oriented in the opposite manner. So we are actually going to get a different group here. Z2 direct product with Z3 is isomorphic to Z6, but there is one other group of order 6, which is D3, right? Which is isomorphic to S3 in this case. So it does satisfy the first two relations, you'll recall. We have an element which squares to the identity and an element which cubes to the identity. However, that third relation is not going to hold. Okay, so if we start here and we call the purple edge A and the pink edge B. So if we multiply by A, we end up here. Then we multiply by B, we end up there. Then A again, we end up here, and then B again, we end up there. And notice how this does not look the same as the relation that we had before. It in fact is a different relation. And so we have a group of order 6 which is defined by the same generators and 2 of the 3 same relations, but a third, alas, different one. So here's the Cayley graph. As suggested by the Cayley graph, our fifth and final way of looking at D3 is as a group presentation in terms of the generators A and B and the relations A cubed, B squared, AB, AB. So that D3 is once again equal to the presentation given by X and Y. And this is to say that it is equal to the quotient, or isomorphic to rather the quotient of the free group on X quotiented out by the normal subgroup generated by the relations Y. If you're interested in the case of n not equal to 3, generally the dihedral group of order n is a subgroup of the symmetric group of order n. An interesting subgroup, and it is of course the group of symmetries of a regular n-gon in the plane, and it can be generated with just 2 elements and is given by the group presentation defined by these 2 generators and a to the n b squared ab ab as your relations. So d sub n is given by this group presentation. Ladies and gentlemen, the dihedral group. It's not always obvious why we study things from the outset, but I hope that at the end of this elementary group theory series, you have, well, first I hope you've learned something, and second, I hope that you appreciate why we studied groups in the first place. Because it is one of those subjects where you need some background before it really makes sense why it's so far-reaching and why it's so beautiful. Groups are the centerpiece in a room of algebra and geometry, symmetries and symbols. Groups are what bring them all together. I hope you like this series. Leave a comment or email me. It's been fun. Adieu.